All right, first, we need to understand what the problem is asking again. So, if we're given a stoichiometry problem or a balancing problem or anything where we need to know about naming, we need to break this stuff down. So, first and foremost, let's just say, for example, I need to know how to name FeCl3. Well, the common thing that we would normally do for transition metals is transition metals have Roman numerals. And so if we break it down a little bit further, we need to know a few characteristics about transition metals as well as nonmetals. And for transition metals, what we can do is we can break this guy up into a Fe3 plus and Cl minus. Now, you may be wondering, where did I get this minus from? Well, there's a list. If you can imagine, in my fantastic periodic table I'm about to draw, if we have this here, it's my periodic table, very, very rough representation. But essentially, let's imagine that we have this column here. This is going to represent +1. This is going to be +2. We're going to say that this varies. And then we have essentially boron, carbon, all right. Then we have nitrogen, oxygen, and we're going to erase some of this real quick. And we're going to get rid of that. Go back to this, oxygen and fluorine. Okay. The reason why I picked these specifically is because when we're trying to figure out charges, this is the best way to go. And then basically this large portion here will be your noble gases. So we'll call this Ng. Over here though, what we want to do is break it down into charges. Now these charges are important. The reason why these charges are important is because they reflect on the configuration to strive to get. So here we have +3. This is going to also be varied. This is going to be -3. This is -2. This is -1. And so what we want to remember is that since fluorine is right at the top, and then chloride in this case is going to be right underneath fluoride, F minus, we want to break it down this way. So if we go ahead and cross these this way as much as we can, we'll get the same structure in this orientation. So this is actually going to be called iron 3 chloride. Now remember that transition metals take on the charge that is placed on them. So the Roman numeral represents the overall oxidation state, or you can imagine a charge on that metal. Same thing if we were to try to do something like FeCl2, right? This would be Fe2 plus, and we have Cl minus. All right. So as we keep going, if we look at this a little bit further, I mean, we can pretty much break this down as much as we can. Let's think about some other transition metals. Let's say, for example, copper 2 sulfate. Copper 2 sulfate is this guy right here. Now, if you remember your polyatomic ions, or in this case, this is a polyatomic anion, sulfate is going to be SO4 2 minus, and then copper is going to be copper 2 plus. We can use the cross method to basically figure out which side these are going to be on. And so due to the fact that non-metal reactions tend to use the empirical formula state, we can go ahead and do Cu2SO4 parentheses 2. Now this is not the empirical formula. What we want is the empirical formula. Now to get the empirical formula, we need to reduce it, find a common denominator. So to find a common denominator is going to be divided by 2 here. Therefore, what it's going to end up being is copper sulfate, as we had seen before. Okay, we can try another one. Let's try another one real quick. We can do, let's say, manganese. We could do something like manganese, but instead of doing manganese, something a little bit more simpler. Let's just do a regular metal, which basically those are going to be slightly different. For regular metals such as alkali / alkaline earth metals, they do not use a Roman numeral. What we want to use for them would be, say, for example, if we have magnesium chloride or magnesium bromide, that will do magnesium bromide would be this. Now, how do we break this up again? Well, it's Mg2 plus and Br minus. All right. So that's how we want to remember this. We also can keep going. Let's say we just do MgF2. This is magnesium fluoride. Okay. Or if we do a more common one like calcium chloride. So it can also be very useful. Okay. So you always want to try to break it down as much as possible. Let's think about trying to combine these guys. Let's say, for example, I have this plus, let's say, this, for example. So this would be silver nitrate. This is technically silver 1 nitrate, but it's assumed because that's the most common oxidation state for silver 1. You also have calcium chloride. So what we want to do in order to figure out what the potential products are, we want to break it down into its ions. So its ions are going to be Ag plus NO3 minus, and then we have plus. Basically, it looks like as if I'm breaking it down to an ionic equation, but I'm not going to fully make it an ionic equation here. So what we want to do is we want to do inside out, outside in method, where we take essentially these guys and pair them up. And so what we will get is that when we do that, we'll get silver chloride plus calcium nitrate. Okay, now as you can see, this is not balanced, so we will unbalance this. So we have 1 chloride over here, 2 over here, so we can put 2 here. We have 2 silver now. We need a 2 over here. Now this is 2 silver, 2 nitrates, 1 calcium, 1 calcium. This is good to go. This is how you want to represent this problem. Okay.